which is also an outreach activity of the department. Friends, we have been hearing many stories about Ramanujan, but this session becomes very special when we are going to listen from a person who himself deserved to be a part of these stories. So we thank Professor Bruce Berndt to kindly accept our invitation. Now I request Dr. Vivekanand to introduce our guest speaker. Thank you.
Thank you, Dr. Ashisha, for giving me this opportunity. It's my honor to introduce Professor Bruce Berndt. Professor Bruce Berndt is one of the world's foremost mathematicians in the work of Srinivasa Ramanujan. He received his PhD from the University of Wisconsin in 1966. After an assistant lectureship at the University of Glasgow for 1 year, he joined as an assistant professor at the University of Illinois in 1967. In 2012, he became a fellow of the American Mathematical Society. In the same year, Professor Berndt received an honorary doctorate from Shastra University. During his 52 years of teaching and research at UIUC, he has supervised 37 doctoral students and 10 postdoctoral students and published more than 270 research papers. Even now, he is actively involved in writing research articles. In 1996, prize from the American Mathematical Society for editing the notebooks of Ramanujan, which was a quite monumental work. He published 5 volumes on Ramanujan's notebook, and then together with Professor George Andrews, he published 5 more volumes on Ramanujan's lost notebook. Professor Berndt is the founding editor of the International Journal of Number Theory. He is also an editor of the Ramanujan Journal, which is an international journal devoted to the areas of mathematics influenced by Ramanujan. Today, he will be speaking on the life of Ramanujan and his association with Ramanujan and his mathematics. Now I request Professor Berndt to start his lecture.
Thank you very much for the introduction. If at any time you can't hear me or see me, please let me know. It is unfortunate that I cannot join you in India for this talk because of the COVID crisis. Let me just say that our thoughts and prayers are with all those who have lost loved ones and who have suffered serious illness and or encountered economic hardship due to the virus. In particular, let me just say that my good friend Bhargava at the University of Mysore lost his wife Ratna just 2 or 3 weeks ago to COVID illness. So here's an outline of my lecture. I will discuss Ramanujan's life and then give a history of the notebooks and tell you about my interest in the notebooks and how it started. I'll give some examples from the notebooks, and then I'll go to the lost notebook and give its history, and then I'll give some examples from the lost notebook. So first, let me give a brief account of Ramanujan's life. He was born in Erode, in the home of his maternal grandmother. After 2 weeks, or 2 months, I should say, he went to Kumbakonam with his mother, and this is where he lived for the majority of his life, in particular up to about 1910, when he moved to Madras. So this is the most famous photograph of Ramanujan. It was taken in 1919, prior to his return to India. Ramanujan was very ill at the time, and it looks like the photograph is given in terms of a suit coat, but in fact, this is a bathrobe, and these are pajamas. He was too sick to go to the photographer, and the photographer had to come to the nursing home in which he was a patient. So this is the most famous picture of Ramanujan, but it really doesn't show him the way he was for most of his life. This was taken a few years earlier in Cambridge. It's excised from another photograph, and you can see that by the time the passport photograph was taken, he had lost a considerable amount of weight. There are just 4 photographs that actually exist of Ramanujan. So these are 2 of those. In 1987, I had the privilege of going to Kumbakonam with Balasubramanian from Madras. And this is Ramanujan's original home. This is one of the most thrilling experiences of my life, to see the home as it probably was when he lived there. If you go onto the porch, just behind that bamboo curtain, if you carefully look above the doorway, you will see a photograph or a picture of Ramanujan that was cut from a local newspaper. And this is the only indication that this was the home of India's great mathematician. Now the home has been turned into a museum. I can understand that the home should be preserved for posterity. However, for myself, it was much more exciting for me to actually see the home as Ramanujan actually, where Ramanujan lived. Ramanujan, as most school children did in those days, worked on a slate. And this is actually the slate that Ramanujan used. It's in the family of S. Narayana Iyer. In a few minutes, I'll tell you who S. Narayana Iyer is and his influence in Ramanujan's life. So here's my favorite picture of myself holding Ramanujan's slate. So Ramanujan, as I said, worked on a slate, and at the age of 12, he borrowed Loney's Plane Trigonometry from an older student. The book has much more in it than you would expect from the title. In particular, there's some work on calculus and infinite series. And then just before he entered the government college in Kumbakonam, he borrowed Carr's Synopsis of Pure and Applied Mathematics from the library. And this is a very unusual book. It contains over 4,000 results with hardly any proofs. Carr used this in his tutoring of students in Cambridge and London. So about the time he entered the college at Kumbakonam, he began to record the results of that he found in notebooks. So there are several reasons why it has been suggested that he didn't write any proofs, but he only recorded the results themselves. So here are 4 reasons that have been suggested for why Ramanujan didn't write his proofs. So probably the most common suggestion is that he was influenced by Carr's book, which, as I said, gives a succession of over 4,000 formulas without proofs. Paper was expensive. He worked like a slave, as other students did. He really couldn't afford the paper. The paper that he had for his notebooks probably was expensive. And then thirdly, his theorems were only a personal account of his discoveries. Ramanujan felt there was probably no need to record the proofs. If someone asked him, how do you derive a certain formula? I'm sure he could, tell the person asking the question, how he derived a certain result. So from his own, for personal reasons, there just wasn't really any need to record the proofs. Now, some people have suggested that he did not have proofs and he derived his results from religious inspiration, particular goddess Namagiri. So I agree with the last part that he probably felt as many would, that he was religiously inspired by goddess Namagiri, but Ramanujan had proofs like any other mathematician. Now, maybe they weren't rigorous. So, for example, maybe he inverted the order of summation and integration and didn't justify it. However, he knew when his formal processes, inversion of limits, for example, worked and when they didn't work. So he really had proofs like any other mathematician, but at times maybe they weren't rigorous. He didn't justify all the steps rigorously. Well, Ramanujan didn't pass his exam at the end of his first year at the Government College of Kumbakonam. And from about 1904 to 1910, he really was out, didn't have employment. He married in 1909 and then moved to Madras shortly thereafter. He obtained some financial support from R. Ramachandra Rao, who was a mathematician and collector in the Madras Civil Service. And then in 1912, he obtained a job at the Madras Port Trust office as a clerk in the accounts department. And the chief accountant there was S. Narayana Iyer. So S. Narayana Iyer was actually one of the best mathematicians in India at the time. So he could appreciate Ramanujan's work, and he encouraged Ramanujan, along with the chair of the Madras Port Trust office, Sir Francis Spring, to write to English mathematicians about his work. So he wrote 3 altogether before writing Hardy. In particular, he wrote Baker and Hobson, who were both mathematicians at Cambridge, but neither evidently replied to his letter. He also wrote M.J.M. Hill, a professor in London, and he replied, but it was clear that he really didn't quite understand what Ramanujan was trying to communicate in his letters. And then, as most of you know, he wrote Hardy, who appreciated Ramanujan's results. In particular, in his first letter to Hardy, Ramanujan gave him over 60 of his theorems. Hardy replied that trying to get him to come to Cambridge to further his work, he was very reluctant to do so because of family religious objections. For example, crossing the seas would make him, so to speak, unclean. He wouldn't be able to attend, another wedding or a wedding after he returned, for example. So Hardy wrote him again, and Ramanujan replied again with another 60 theorems. But eventually he obtained the permission from his parents, in particular his mother, and he also had a pilgrimage to the temple of the goddess at Namakkal, and there he obtained then permission. He was inspired then to accept Hardy's invitation to come to Cambridge. So before he left for Cambridge in March of 1914, he traded slates with S. Narayana Iyer. So I am told that this is a sign of respect if you trade slates or if you give your slate to another person. So clearly Ramanujan had great respect for Narayana Iyer. And in fact, the two of them actually worked together during the nighttime or evening after Ramanujan and Narayana Iyer completed their work at the Madras Port Trust office. So now the slate is in the possession, I think, of the great-grandson of S. Narayana Iyer. Yeah. So here's a photograph of Hardy. It's probably the most famous photograph of Hardy. One reason I don't like the photograph is that he appears to be holding a cigarette in his hand. And here is a photograph of Hardy and Littlewood. So unfortunately, Ramanujan's stay in England coincided almost exactly with World War I, and Littlewood was away working on ballistic missiles during this time, and unfortunately then didn't have much contact with Ramanujan. Well, let me just give a few results from Ramanujan's first letter to Hardy. So he says 1, 2, 4, 5, 8, 9, etc. are numbers which are either themselves squares or can be expressed as the sum of two squares. And then he says the number of such numbers greater than A and less than B is equal to this expression. K is 0.764, etc. Theta x is very small when compared to the previous integral. And K and theta of x have been exactly found, though complicated. I've quoted exactly as it Ramanujan wrote in his letter. There's a slight misprint here. This should be theta of b, of course, instead of theta of x. Then. So in Ramanujan's notebooks, he has quite a bit of information about this result. In fact, he actually gives his proof in his notebooks, and it's only the one of a couple proofs in the entire notebooks. And in fact, it takes up almost a page. So again, this result occupies, so to speak, more space in his notebooks than really any other result. So about this result, Hardy said the dominant term, giving it in Ramanujan's notation, was first obtained by Landau in 1908. Ramanujan had none of Landau's weapons at his command. It is sufficiently marvelous that he should have even dreamt of problems such as these, problems which it has taken the finest mathematicians in Europe 100 years to solve, and of which the solution is incomplete to the present day. So this really is a remarkable achievement because, you know, most of us rely on when we do research with those who have come immediately before us. So in other words, what we've done is part of a continuous development, usually, of the subject. Of course, there are, you know, leaps forward, but here Ramanujan made, so to speak, a leap entirely over the history which is, in which this study was made. Ramanujan's optimism was, he had a little bit too much optimism in terms of the error that was made. That constant in front of him was correct, and he gives a formula for it in the notebooks. Excuse me, let me state another result from the first letter. This is one of my favorite results. So Ramanujan defines this integral phi of n. And here's the same integral with the sine instead of the cosine. And we have sort of a theta inversion formula here, because here is phi of n, and here's phi of pi squared over n, like you would in a theta function transformation. And he gives several values of this function. They are very interesting in themselves. You can see some are algebraic numbers, and a couple of them involve pi. So, you know, the question is, which ones involve pi and which ones don't? I don't think this has ever been sufficiently answered then. So, as indicated, Ramanujan went to Cambridge in March of 1914. Already, as you can see from this letter that he wrote to a friend, that, you know, he, at the end of his first year there, he was not, you know, in good health. So he says to his friend, I was not well to the beginning of this term owing to the weather, and consequently, I couldn't publish anything for about 5 months. And then 2 years later, Hardy, in a letter to Mittag Leffler, Swedish mathematician, Ramanujan had become more ill, and he says, you will be sorry to hear that Ramanujan is seriously ill, and that we are very much alarmed about him. In the following year, his health returned somewhat, and Ramanujan was elected as a fellow of the Royal Society. So I've listed here those in the Royal Society, mathematicians or physicists in a couple of cases, who approved his election. Those that I've emphasized in italics were not present actually at the meeting, but voted for him. And note that Hobson and Baker voted for him. Recall that Hobson and Baker were mathematicians that Ramanujan wrote before he wrote to Hardy, and they never replied then. So in particular, Hardy, in this letter to Francis Dewsbury, the register at the University of Madras, said in November of 1918, "There is at last, I am profoundly glad to say, a quite definite change for the better. I think we may now hope that he has turned the corner and is on the road to a real recovery. His temperature has ceased to be irregular and he has gained nearly a stone in weight. The consensus of medical opinion is that he has been suffering from some obscure and only partially diagnosed source of blood poisoning, which is now dried up." So there has been a lot of controversy about Ramanujan's illness and exactly what it was. So Ramanujan was mainly treated for tuberculosis, and when he returned to India the following year, he was treated with tuberculosis. A medical doctor in England many years later suggested that Ramanujan died of dysentery because it was not treated properly. From the descriptions of Ramanujan's health prior to his coming to England, it appears that he had dysentery actually twice. And this doctor, Dr. Young, felt that if dysentery is not treated properly, the germs tend to live in your large intestine, and they can just stay there for a while. But if your life has been disturbed, as Ramanujan's certainly was when he went to a colder climate, the amoeba or germs could act up again and kill you. So that was his opinion. Most people, I think, in India have always felt they died of tuberculosis, and I can't judge whether they are right or whether Dr. Young was right. So as I indicated, Ramanujan returned to India in March of 1919. After he returned, he only wrote one letter to Hardy. So let me just quote from part of it, and I'll actually say more about this letter later when I talk about Ramanujan's lost notebook. So I discovered very interesting functions recently, which I call Mach theta functions. Unlike the false theta functions studied partially by Professor Rogers in his interesting paper, they enter into mathematics as beautifully as the ordinary theta functions. I am sending you with this letter some examples. So I'll indicate later what false theta functions are, and also what theta functions are, and a little bit about what Mach theta functions are. Well, Ramanujan died on April 26, 1920, at the age of 32. And after he died, Hardy and others advocated that his published papers be brought together and also his notebooks be published as well. So unfortunately, the London Mathematical Society was evidently in poor financial condition for some years, and so his collected papers were not published until 1927, and his notebooks were not published as well. So here is the title page for the collected papers, and there is something very unusual about this title page. I'll give you a few seconds and see if you can see what's unusual about this title page. Well, it's unusual because note that Wilson's name is in slightly larger print than that of Hardy, and P.V. Seshu Iyer, who was Ramanujan's teacher at the Government College of Kumbakonam in the 1 year that Ramanujan attended the college. So evidently, in fact, Hardy referred to this later, B.M. Wilson was the primary person in bringing together Ramanujan's papers for this volume. Okay, so let me give a little bit of history behind Ramanujan's notebooks as to what happened to them after Ramanujan died. So Ramanujan actually, when he came to England, had one notebook. So in this letter to his friend S.M. Subramanian, he said, "I am doing my work very slowly. My notebook is sleeping in a corner for these 4 or 5 months. I am publishing only my present researches as I have not proved the results in my notebook rigorously." So when Ramanujan returned to India, he actually left this first notebook with Hardy. And evidently, shortly before he returned, he made a second notebook, which was a revised, enlarged edition of his first notebook, but it contains many more results than the first notebook. And then on the contrary, the first notebook actually contains around 200 results that are not in the second notebook. So evidently, in the last year or two before returning to India, he again revised and enlarged the first notebook and added results to in his second notebook. And then he also made a third notebook. We don't know for sure if this was composed in England or if it was composed after he returned to India. I tend to think it's the former because it only has 33 pages, and the results in it, which are not organized, are more in the spirit of his first and second notebooks than the results he proved after he returned to India. So I counted the results in Ramanujan's notebooks as I went through them over several years, and I counted 3,254 results, different results altogether. Okay, and this is just what I was emphasizing here. Probably both of these, the second and third notebooks, were written before he returned to India. Now let me quote from a letter of Francis Dewsbury to Hardy. "I have now seen your letter dated 19th November 1921 to Mr. Kayananda Rao, in which you state that you have one of the late Mr. S. Ramanujan's notebooks with you. I shall be glad if you will return the original notebook when you have extracted from it the selected matter for printing in the memorial volume." So in fact, Dewsbury thought that Hardy had a second notebook and he had the first notebook, but it was just the reverse. Ramanujan left the first notebook with Hardy, and what Dewsbury had was the second notebook, and probably the third notebook as well. Indeed, Hardy did return the first notebook to India, and in 1925, a handwritten copy of the notebooks was made at the University of Madras, and this handwritten copy was sent to Hardy. So for those of you who might complain about the slowness of a photocopier, well, just remember that, in 1925, we didn't have photocopiers, and the only thing to do is to copy things by hand. So the notebooks are at the University of Madras. At least I was at the last time I inquired about them. So these are the 3 notebooks. Evidently, they were not kept in a humidity-controlled environment, and insects began to destroy some of the pages. So the pages were laminated to prevent further destruction. So in 2012, well, let me say a little bit more about the editing of notebooks. But in 2012, a new edition of the notebooks was made, and it was told at the time that, in fact, the lamination of the pages shouldn't have been done because that was cracking, and the pages were still suffering from a lot of damage. Well, as I said, the notebooks were copied and sent to Hardy. And then in 1928, B.M. Wilson and G.N. Watson agreed to begin to edit the notebooks. And Watson made a handwritten copy of the handwritten copy that was sent to Hardy. So Wilson, again, remember, he's one of the 3 editors of Ramanujan's collected papers, worked on editing the notebooks for 5 years, but unfortunately incurred an infection in the hospital where he went for a routine hernia operation and died in the hospital. And then Watson worked on editing the notebooks for over 10 years, but eventually he stopped. In particular, Watson worked on Ramanujan's work on modular equations, proving most of the results on modular equations. I'll define a modular equation in just a few minutes. So it wasn't until 1957 that the notebooks were actually published. And this is a copy of my copy of the notebooks. And then, as I indicated, in 2012, another edition was published. So this edition is much clearer. However, I should say that the Tata Institute's original publication there were only a few places in it where I had trouble reading Ramanujan's work. But this one indeed is a better publication, clear publication. But let me tell you about my interest in Ramanujan's notebooks. As was indicated in the introduction, I got my doctorate at the University of Wisconsin. I never had a course in number theory until the spring semester of my 3rd year at Wisconsin. And I took a course in modular forms from Rod Smart. So this is the first time I ever studied number theory. And the reason I took the course was because at that time I was mostly interested in complex analysis, and I had heard that modular forms involve a lot of complex analysis. So I really enjoyed the course, and I asked then Smart to be my thesis advisor. And then in the following semester, so this would have been the fall semester of my 4th year at Wisconsin, I took a course from Marvin Knopp in modular forms with applications to number theory. And it was here that I learned about Ramanujan's and his work for the first time. In particular, Marvin proved Ramanujan's congruences for the partition function, and he also discussed Ramanujan's and Hardy's asymptotic formula for the partition function. I never took a course from Richard Askey, but he remained a strong influence in my life up until he died 2 years ago. I had a lot of Bessel functions in my PhD thesis. Askey was the world's foremost expert in Bessel functions for many years. And I think it was these Bessel functions attracted Askey to my work, and he remained a strong proponent of my work throughout his career and my career. Well, after I received my doctorate, I went to the University of Glasgow for 1 year, where my mentor was Robert Rankin. Rankin was actually Hardy's last PhD student. So one day I was in Rankin's office, and we started to discuss Ramanujan's work, and he told me about Ramanujan's notebooks. So this was the first time that I had ever heard of Ramanujan's notebooks. And he had with him in his office the Tata Institute's publication of the notebooks. And then he offered to me, he said, I'll be glad to loan these notebooks for you if you're interested. And I told him I wasn't interested. Well, I've made a lot of mistakes in my life, but this was certainly one of the chief mistakes that I made when I told him I wasn't interested in the notebooks at that time. Yeah. Well, after my 1 year in Glasgow, I took a job as an assistant professor at the University of Illinois. The head of the department was Paul Bateman, who was a very famous analytic number theorist. And I think perhaps in my 3rd year, he asked me to referee 2 papers by EMO Grosswall. So being relatively famous and the head of a department, he obtained lots of papers to referee, and he didn't have time to referee these 2 papers, so he gave them to me to referee. Okay, as you can see, I did recommend acceptance. But this was the first time that I had ever really read about any of Ramanujan's work from the notebooks. So in these 2 papers, Grosswall proved some of the results in Ramanujan's notebooks. So here is a photograph of Grosswall. Let me just tell you about one of the formulas that Grosswall proved. Its famous result of Ramanujan is formula for the Riemann zeta function at the odd integers. So here alpha and beta are positive integers such that their product is pi squared. Ramanujan loved symmetry, so if he could express his findings in terms of symmetry, he would do so. So note here, this expression in brackets or parentheses is the same as this one, but alpha is replaced by beta. The B, 2K are Bernoulli numbers. So if you set alpha and beta both to be pi and replace n by 2n plus 1, you get this formula for zeta 4n plus 3. So this special case is actually due to the Czech mathematician Lerch in 1901. This is one of my favorite results because, see, the Bernoulli numbers are rational numbers. So here we see that zeta 4n plus 3 is almost, I'm speaking very loosely here, of course, a rational multiple of pi to the 4n plus 3. Well, it's almost because we have, so to speak, an error term. We have to add this rapidly convergent series. So as most of you know, zeta of 2n is a rational multiple of pi to the 2n, where the rational multiple involves the 2nth Bernoulli number. So this formula, the other formulas that Grosswall proved are in chapter 14 of the 2nd notebook. And here is a photocopy of that page where these results appear. Here is that original formula for involving zeta of 2n plus 1. So I spent my first sabbatical at Illinois at the Institute for Advanced Study in Princeton. And in February of 1974, so this was the academic year 73-74 that I was at Princeton, I was working on transformation formulas involving Eisenstein series. And all at once I saw that these results that Grosswall proved and that I was proving at the time were in the notebooks, or I could prove these results from the notebooks. So this was really a joyful moment for me that I could prove these results. And so I went to the Institute library, and unfortunately they did not have the Tata Institute's publication, but the Princeton University Library did. So I checked out the notebooks, found a few more formulas I could prove, but a few thousand others that I did not know how to prove. So when I returned home after my sabbatical, one of the first things I did was to write the Tata Institute and get a copy of the notebooks. So it only cost me $25, including shipping, in this wooden case here for these notebooks. Man, it's a great deal. Where can you get 3,000 theorems for $25? So I didn't really do anything with the notebooks further, except I proved a few more results, and I used my methods that I was developing at Princeton and a few more papers. But in May of 1977, when the semester ended at the University of Illinois, I just said to myself, let's try to prove every result in chapter 14. This again is the chapter in which the formulas that Grosswall and I proved are found. So there are 87 results in this chapter altogether. So I worked on this for over a year. I had help from my first PhD student, Ron Evans. And then George Andrews visited Illinois, and he told me that the work that Watson and Wilson did in editing the notebooks had been preserved at Trinity College, Cambridge. So I wrote Trinity College and asked for a copy of these notes, and they kindly sent them to me. So I decided that I would go back to the beginning of the second notebook, and I just gradually over the years, with the help of several of my graduate students, then worked my way through the notebooks. And I finished the editing in about 1999. So I spent about 22 years altogether proving the results from the notebooks. So I'll indicate a few topics from the notebooks. So there's a lot of results due on Q series. So Q series have in their summands products of this type. AQ sub n is the product of 1 minus AQ to the k running from 0 to n minus 1. So not all Q series have such products in their summands, in particular theta functions, which are part of the theory of Q series, and I'll define these in just a moment, don't have these in their summands. So this is the infinite version. You just let n tend to infinity. Excuse me. This Q is what is called the base, and if it's fixed throughout a discussion, we eliminate it from our notation. So Ramanujan actually never used the product notation. He would just write out the first few terms of the product. So this is the general theta function as Ramanujan defined it. This is not the classical definition due to Jacobi, but for Ramanujan purposes, this was the best definition. So this particular formulation or definition was not given in the literature before Ramanujan gave it. And for his purposes, symmetry, for example, this was the best definition. So this is what's called the Jacobi triple product identity here. And the three most useful and famous special cases are phi of q. So this is when A and B are both equal to q. And psi of q, I've folded up the negative index terms with the positive index terms. And then f of minus q, again, I folded up the negative index terms with the positive index terms. Okay, these are the triangular numbers, and these exponents are the pentagonal numbers. Okay, as I indicated, Ramanujan actually never used this notation, and he didn't use any of the standard notations for theta functions. He derived many properties of elliptic functions, but he didn't use any of the standard notation for elliptic functions as well. And it's always been a mystery as to if Ramanujan ever saw or read any book on elliptic functions, or if he just derived everything without knowing that they had previously been discussed in the literature. Okay, let me define a complete elliptic integral of the first kind. So it's given by this expression. If you expand the integrand in a binomial series, you get this expression. This is a hypergeometric function. So in here, I'm using the rising factorial or the shifted factorial notation then. So K is called the modulus, and here K prime, the square root of 1 minus K squared, is called the complementary modulus. So this next definition might seem a bit weird to some of you, but it's very important in the theory of elliptic and theta functions. So K, K prime, L, and L prime, they're complete elliptic integrals associated with these moduli, K, K prime, L, and L prime. So suppose we have a relation of this type amongst the elliptic integrals. N is a positive integer. Then a modular equation of degree n is a relation between the moduli K and L, which arises from this definition, or this equality. So Ramanujan sets alpha to be K squared and beta to be L squared. So we'll use his notation here, whereas in the classical notation, the K and L are used. So this is really how Ramanujan thought of a modular equation. He didn't think of it really in terms of elliptic integrals, as is true in most of the literature, but in terms of an equality involving hypergeometric functions. And here are three of Ramanujan's modular equations, degrees 3, 5, and 7. So note the beautiful symmetry in these first two modular equations of degree 3 and in the other two modular equations. Ramanujan loved modular equations. For degrees 3 and 5, he had over a dozen modular equations in these degrees. In fact, in his notebooks, he had well over 100, almost 200 different modular equations. So a modular equation of degree 3 doesn't appear in any of the other degrees. In other words, these modular equations for prime degree are unique. So here is a modular equation of degree 5. You won't find this modular equation anywhere else in terms of the theory of modular equations. So this is a huge topic in Ramanujan's notebooks, and he obviously loved modular equations. So this is a very complex result from Ramanujan's notebooks, and I've stated it in with more contemporary notation. I will, in the next slide, give you a special case. But what I want to emphasize is the unusual nature of this result. So here we have actually a theta function, but really only the indices from 1 to infinity. So note, if I let x tend to 0, then these expressions tend to 1. And in other words, we're heading towards a divergent series. So Ramanujan gives a representation for this, and this is a continued fraction. And then he gives an error term, and the error term, a further error term after you truncate this finite sum, is big O of x to the 2n. So in other words, it's of the order of a power of x, x to the 2n power as x tends to infinity then. So this is very unusual in the fact that he's linked together a continued fraction with a theta function series. Now, one of the reasons I mention this is that a special case actually occurs in Ramanujan's second letter to Hardy, namely when A is 1 and B is a half. So here we again, this is the continued fraction. So you can think of this as an evaluation of this nice, beautiful, simple continued fraction as a theta function. And then here's the error term, which I mentioned, and Ramanujan says nearly. So he really had the idea of an asymptotic series, and when he truncates it, he used these words nearly and very nearly frequently when he had approximations to his results or asymptotic series. So this is what I wanted to emphasize, the unusual nature of this kind of formula and the fact that Ramanujan gave very good approximations, and he would always usually say nearly or very nearly after his approximations. I'm going to skip this next result for lack of time. So let me just indicate then, so I was just checking my time here. Okay. Let me just indicate or give a summary of topics in Ramanujan's notebooks. So there are lots of identities, especially involving infinite series. A lot of work on theta functions and elliptic functions. So the main, if one asks what is the main topic of the notebooks, the main topic would be theta functions. And modular equations arise from theta functions. They're also equivalent to theta function identities. There's a lot of work on hypergeometric series. I've only given you one of them. A lot of work on Q series and what are called basic hypergeometric series. Again, these are series with these Q products in the summands. A lot of results on integrals, asymptotic expansions, which I just mentioned, and a lot of continued fractions. And so most of the results on continued fractions are new. Let me just say a few words now about, how many results are new, how many results are not new in the notebooks. So Hardy said that 2/3 of the results in the notebooks were previously discovered by others. I find this much too high. So yeah, I didn't make a copy or didn't make a summary of the results that are new, but certainly well over a half, probably well over 3/4 of the results in Ramanujan's notebooks are new with Ramanujan. And there's also some number theory in the notebooks, as I just indicated at my beginning of the discussion of Ramanujan's first letter. Okay, so I think this is all I'll say about the notebooks and the expressions in the notebooks. So let me now say something about Ramanujan's lost notebook. So let me quote from the Bhagavad Gita: "Through long lapse of time, this knowledge was lost." So I'm reinterpreting the knowledge being the lost notebook. "And now, as you are devoted to truth," this is George Andrews, "I will reveal the supreme secret, namely the lost notebook." So here is a picture of George Andrews just before he found the lost notebook. So here he is at Cambridge with his daughters, Amy and Katie, and this is Lucy Slater, who is probably the best expert in hypergeometric functions at that time. So Andrews was told, advised by Lucy Slater, that he might find it interesting to examine Watson's papers. And while Andrews was examining Watson's papers in the library at Trinity College, Cambridge, he found a sheaf of papers in Ramanujan's handwriting, and he knew immediately, well, indeed, this was Ramanujan's handwriting, and he knew it was from the last year of Ramanujan's life. So Andrews was very familiar with Ramanujan's last letter to Hardy, and he was familiar with Ramanujan's handwriting from the notebooks. So he knew immediately that this sheaf of papers, which he called Ramanujan's lost notebook, was indeed Ramanujan's work from the last year of his life. So the sheets were of various kinds. This sheet is probably a piece of parchment paper, because when the photographer took a picture of it, he really was taking a picture of both sides of the page, and this is why it's extremely difficult to read. The Lost Notebook was eventually published in 1988. So again, Andrews found this manuscript at the Trinity College Library. So the big question is, how did it reach the Trinity College Library? let me go back to this letter from Francis Dewsbury. It's actually a second letter to Hardy. So in the first part, I mentioned before, I think, that he's telling Hardy that he's giving copies, sending him copies of the notebooks. So he has put them in 4 notebooks. But what I want to emphasize now is that Dewsbury wrote, I also forward a packet of miscellaneous papers which have not been copied. It is left to you to decide whether or any of them should find a place in the proposed memorial volume. Kindly preserve them for ultimate return to this office. Hardy actually never returned any of the papers. So unfortunately, Dewsbury and Hardy never made a copy of or listed what was in the shipment, but almost certainly this shipment contained Ramanujan's lost notebook. So sometime Hardy passed on the papers to Watson. We really don't know when. We think it was in maybe the late 1930s when he gave Watson these papers. So in 1936, Watson wrote a paper on the Mach theta functions, which are mentioned in Ramanujan's last letter to Hardy, and which occupy many pages of the lost notebook. So he chose the final problem. Really, it meant the last work that Ramanujan did on the lost notebook, or that he did before he died. And the adventures of the final problem is a famous story by Sherlock Holmes. Yeah. And Sherlock Holmes' sidekick was Dr. Watson. So lots of reasons for the title of his article, and also the title of the last lecture that he gave as president of the London Society. Well, Watson was professor of pure mathematics at the University of Birmingham throughout his career. And after he retired, Robert Rankin assumed the position. And when a position opened up a few years later at the University of Glasgow, Rankin, being a Scotsman, took this position at the University of Glasgow. So after Watson died in 1965, Rankin visited Mrs. Watson, and they discussed what they should do with Watson's papers. And they agreed that what Watson or what Rankin should do is to go up to Watson's attic floor office, which he said later was covered to the depth of about a foot of papers. And he would sort through the papers, and those worth preserving be sent to Trinity College, Cambridge. Watson had always been had an affection and respect for this college. So this seemed the natural place to deposit Watson's papers. So Rankin would take periodic trips to Birmingham to sort through these papers, and he found a lot of material, in particular, the lost notebook of Ramanujan, a lot of material due to Ramanujan. So in fact, in December of 1968, Rankin sent the Ramanujan material to Trinity College, Cambridge, but he never told anyone about it. So for about 7.5 years, it just sat there in the library until, excuse me, Andrews rediscovered it. Rankin was never very fond of calling this material the lost notebook, because he said it wasn't a notebook and it wasn't really lost. I mean, he knew about it and the librarians knew about it. So I'm running out of time, so I'll just briefly discuss a few results from Ramanujan's lost notebook. There are a lot of results on Q series in the lost notebook. So let me just, and a lot of the results are analogs of results on hypergeometric functions. So here is the Q binomial theorem, for example, an analog of the binomial theorem. So I mentioned earlier false theta functions. So, or Ramanujan mentioned these in his last letter to Hardy. A false theta function is like a theta function, but you change the sign of infinitely many terms. So excuse me. So previously I defined Q, psi of Q, I'm sorry, as this infinite series without the minus 1 to the n. So this would be a false theta function. And if you truncate a series of a theta function, this is what's called a partial theta function. So this would also be a false theta function by extension of the word false. And this is a more the extended version. It's the first letter to Hardy. It contains much more than I'm writing here. But here, Ramanujan says, the series above is the reciprocal of a theta function, and it has a certain behavior as you tend to Q equals 1. So if you have a certain behavior of this type, it's only true for theta functions. And Ramanujan is telling Hardy, it's not only true of theta functions, there are other functions that exhibit the same kind of behavior as theta functions. So he called these mock theta functions. Okay, I'm running out of time, so I'm going to skip a few things. So as I said, the Lost Notebook was published in 1988 by the Tata Institute. And this publication includes lots of other fragments of Ramanujan partial manuscripts. And undoubtedly, these were in the shipment that Dewsbury sent to Hardy. And then there are several manuscripts of Ramanujan that no longer exist, but were copied by Watson. So in particular, these 7 manuscripts of Ramanujan, or partial manuscripts, were copied by Watson. And for the most part, we don't have the original manuscripts of Ramanujan. Okay, if you'll give me a few more minutes, is it all right if I talk for a couple more minutes, and then I'll stop here. And I'll discuss a very famous problem in how
You can take it's okay, sir. You can continue. Yeah.
Okay, I'll try to conclude in 5 minutes then.
Yeah, it's okay. It's
okay. So this is one of the famous unsolved problems in number theory, and Ramanujan evidently worked on this problem. So I'll go back to squares, which I opened our discussion of Ramanujan's mathematics, but now in a different sense. We'll let R2 of n denote the number of representations of the positive integer as a sum of 2 squares. So we count different signs and different orders of the summands as distinct. So 5 is plus or minus 2 squared plus or minus 1 squared. You can invert the order. So in other words, R2 of 5 is 8. Yeah. And each representation of n as a sum of 2 squares can be associated with a lattice point in the plane. So for example, if we take this representation, we associate it with a lattice point minus 2, 1. And then each lattice point can be associated with a unit square on which the lattice point lies. So it doesn't make any difference which one we take, but I'm always going to choose the unit square where the lattice point's in the southwest corner. Okay, so here then are the colored lattice points, or colored squares, in a circle of radius square root x. So you see the number of representations of R2 of n, if I take n less than or equal to x, is approximately the area of the circle then. But of course, it's obviously not going to be exactly the area of the circle, and because we have parts of these squares outside the circle and parts that aren't colored inside the circle. So this was first studied by Gauss. And again, the pi times the radius squared, pi x, is a good approximation for this sum. But there's going to be an error term. So we put a prime on the summation to indicate that if x is an integer, we only count half of the term. And the reason we do this is because in analytic studies of R of x, this is the one which with the prime which appears. So Gauss said, well, all of these squares are in a circle of radius square root x plus square root 2. So we have this bound. And if you take a circle of radius square root x minus square root 2, that's completely covered red. And so from these two inequalities, you get this then. So in other words, the error term is less than a constant times the square root of x for all x then, for x sufficiently large then. So here I've explained the notation, the big O notation in terms of functions, say f and g in general. So Hardy was also keen on this problem. So he wrote a famous paper after Ramanujan arrived in Cambridge on the circle problem. So in particular, Hardy stated this series representation for the error term P of x. And he says the form of this equation was suggested to me by Mr. S. Ramanujan, to whom I had communicated an analogous result for the divisor function. I've always found this a very strange result, because, or comment by Hardy, because if you have a formula, you're not going to say, you know, I can guess there's a formula in terms of Bessel functions. You either have it or you don't have it. So I'm sure that Ramanujan just gave Hardy this result. So you can use this formula to get results for the error term, and mathematicians indeed have always used this formula. So I won't go into what we know about it. But what I want to briefly discuss is Ramanujan's approach to this famous problem. So here is a famous formula for R2 of n. This is, some of you have probably proved this in a course in elementary number theory. So I'm going to take the summatory function and replace the R2 of n by this result, which I write in terms of a sine function. So I have so n I'm writing as the product dj. So we're summing over all pairs dj less than or equal to x. And if I sum on j first, that's just going to be square brackets of x over d, where this is the greatest integer function. And here are two results from Ramanujan's lost notebook. This is really just a partial manuscript that was published with Ramanujan's lost notebook. So Ramanujan gives a formula was similar to a formula that I showed you earlier from Hardy's paper, but it involves a double series of Bessel functions and involves another variable. So this was first proved by my former student Sun Kim and my colleague Zaharescu in 2013. Here's a picture of Zaharescu, and here's a picture of Sun Kim. Picture of Sun is more recent than that of Zaharescu. Okay, so here is what looks like the formula again. So here I'm saying that Zaharescu and I proved this in 2006. Well, you're probably saying out there, why did I say it was first proved in 2013 by Sun, Alexandru, and myself when I first proved it in 2006? Well, if you look at this formula more closely, sorry here, what I've done is to exchange the order of summation here. It turns out that the method of proof that Zaharescu gave and I in 2006 can't be used at all to prove Ramanujan's formula the way we stated it. Yeah. So that's the reason for the two different formulations then. So again, this was the formula that Ramanujan gave to Hardy. If you take theta to be a quarter, that series actually reduces to this after a bit of work. So the question is, can we use this extra parameter theta to attack the circle problem? The circle problem being, what is the correct order of magnitude of this error term? So I think Ramanujan indeed did do this, but we don't know what his thinking was. And I've never been able to use this formula at all to attack the circle problem. Okay, so I think I will, quit here and just tell you about the second identity, which appears on this page in the lost notebook. So this is connected with the divisor problem. So remember, Hardy said there's a similar formula for d of 1 through d of n. And then Ramanujan has a two-variable extension of that formula. So these are different kinds of Bessel functions. And instead of a sine, we have a cosine. So this was even more difficult to prove. So this was proved by Zarescu's former student, Junxian Li, and Zarescu and myself. And we borrowed the title from Watson. And the reason we chose this title is because this is the last result in the notebook, the lost notebook that was to be proved. So Andrews and I went through the lost notebook. Well, for me, it was a period a little over 20 years. For Andrews, it was a bit over 40 years. And this was the last result to be proved. And so this is why we gave this name to the paper. Here's Junxian Li. Well, this really is the last slide in my talk. I apologize that I had much more than I had planned for 55 minutes. So let me just close with some sentences from Freeman Dyson. So we had a celebration at the University of Illinois in 1987 to celebrate the 100th anniversary of Ramanujan's birth. The opening talk was given by Freeman Dyson. He says, I am grateful to the organizers of this conference for bringing me here and giving me a chance to enjoy all the new flowers that have been growing in recent years in Ramanujan's garden. And then in the concluding sentences of his lecture, he said, when I am angry or depressed, I pull down the collected papers from the shelf and take a quiet stroll in Ramanujan's garden. So I would like to add Ramanujan's earlier notebooks and lost notebook to the shelf. I recommend this therapy to all of you who suffer from headaches or jangled nerves. As Ramanujan's papers are not only a good therapy for headaches, again, I would add the notebooks, they also are full of beautiful ideas which may help you do more interesting mathematics. So I'll conclude then with Dyson's advice to you. So thank you very much for this invitation.
Thank you so much, sir, for a wonderful talk. So it was quite thrilling, like we are in the garden of, we can see the results in the garden of Ramanujan. Okay, so now I request students, those who want to ask a question, they can unmute themselves and ask a question. So, sir, I have one question. As you said, most of the people believe, some people believe that even Ramanujan said that some formulas were given by goddesses Namagiri, but like other mathematician, Ramanujan, most of the identities, he knew the proof. Okay. So, but the way he proved, as you said, it may not be as rigorous proof. He may not have rigorous proof. But now we are giving like rigorous proof. But the way we are proving now using modern techniques, okay. But Ramanujan's idea may be, do you think Ramanujan's idea may be different from now our proof?
Yes, let me give two answers. When you ask, when Ramanujan said he got the inspiration from goddess Namagiri, if someone outside of mathematics or maybe not in mathematics, but not familiar with the kind of work Ramanujan was doing, Ramanujan, probably felt that it's really too much to explain to someone who, was outside the field. And so, this is a way of, answering the question for, people might ask him, how he discovered these results. And I think there are some of us who might do similar things today. I mean, many of us are religious, and someone might ask about our work, and somebody might say, well, I was really inspired, maybe by God or Jesus, or somebody from Buddhist religion or something. So it's familiar. It's a lot of us might say things like that. And then getting to Ramanujan's proofs. Yeah. So in some cases we can see, well, how Ramanujan thought, well, especially from the published papers. In other cases, we do not see how Ramanujan thought, and this is the last result that I mentioned in my talk. So for many of the results in Ramanujan's notebooks and Lost Notebook, surely the results, the proofs that we have are not Ramanujan's proofs. They are proofs, in many cases, are verifications. So in other words, we see Ramanujan's formula, but seeing it, then we have an advantage, because we didn't, we weren't like Ramanujan and get it from scratch or his theory. So there are many results, both from the notebooks and Lost Notebook, where we really don't know how Ramanujan thought, and the way we are thinking is clearly not correct. And so, when I was working on modular equations for a couple of years, because there were so many of them, for many of them, I had to use the theory of modular forms, and Ramanujan, as far as we know, didn't know the theory of modular forms. Since I gave these proofs, I think mostly in my third book on Ramanujan's notebooks, others have come along and actually have proved the results without using modular forms. So there are a lot of results that for which we would like better proofs. Yeah.
Okay. Thank you. So I have one more question. Like, most of the identities from Ramanujan's notebook and Lost Notebook, like people have, like you have proved. So are there any other, are there some identities which is still not solved? Some identities of Ramanujan?
I don't think so, but I can't say with 100% surety. I think because the Lost Notebook has, well, in the publication, the Tata Institute's publication, the Lost Notebook itself has something like 120 pages. I'm not sure. I can't remember how many pages it was. But there are almost 400 pages in the publication. So it's easy to skip something. So Andrews and I think we've covered everything, but we're not 100% sure. So for the things that I was covering, I thought this result that I gave at the end was the last result. But I wouldn't swear that I think it's the last result to be proved, but I'm not 100% sure.
Thank you. Yeah. So any other questions or comments? If not, let us give a big hand to Professor. Please unmute and give a big hand to Professor Berndt for.
Thank you. Thank you very much. Yeah.
Thank you. So yeah, so let me end with. So first, I'd like to thank once again Professor Berndt for accepting our invitation and delivering this inspiring talk. I'm sure that this lecture will motivate many young minds to look into the garden of Ramanujan. So I would also like to thank all the students and colleagues for attending this lecture. And finally, the seminar team wants to thank the Department of Mathematics and International Outreach Affair for their support. So with this, we end the talk here. So thank you all of you. Thank you, Professor, once again for giving a beautiful talk. Yeah.
Okay. Thank you.
Thank you so much. Yeah.
Thank you, sir. Thank you.